Okay, so if we're really interested in finding the coordinates of the vertex in the equation of the axis of symmetry for a graph of any function, we want to try and put it in the form f of x equals, let me write this out, we want to try and go for the form f of x is equal to a times the quantity x minus h squared plus k, because once we have that form, we have the location of the vertex itself. So the question would be, well, how would I do that if I'm given a function where it's not in that form? This is in a general form right here, where a is equal to 1, b is equal to 8, and c is equal to 11. Well, in fact, we're going to take advantage of one of the properties that we know, and it's a property of 0. We also call it the additive identity property, and it says this: anytime you take a number and you add 0, it is the same as the original number. It is the additive identity. We're going to take advantage of that additive identity right here, and I'll show you how. What we want to do, notice that we have x minus h squared. Usually when we have that, that is in the form of an equation that has a perfect square trinomial, right? X minus h squared means x minus h times x minus h, and we'd get a nice trinomial. We don't have a perfect square trinomial here, but we would note, if I had x squared plus 8x, I could complete the square. I would get a perfect square trinomial if I took half of 8, squared it, and added it to the end, right? Because we know that x squared plus 8x plus 4 squared, 16, factors as, what does it factor as? X plus 4 squared, right? And that's the kind of thing that we have right here in our form. So how are we going to get this out of this? And the answer is we're going to complete the square in place. Let me show you. I have y equals x squared plus 8x plus 11. So I'm going to move that plus 11 over right here, because if I added 16 to this equation, I would have a nice perfect square trinomial. But I can't add 16 out of nowhere. So what I'm going to do then is that when I add 16, I'm going to subtract away 16 at the same time. And I say, oh my God, Mr. Peoples, what you just did was blow my mind. How can you just add and subtract 16? You're doing nothing to the problem. Well, yes and no, I am doing something to the problem. We can actually just take this piece right here and factor it, because we know that x squared plus 8x plus 16 is a perfect square trinomial factorization of x plus 4 squared. And we're left with negative 16 plus 11 at the end. And so the key right here was that I added and subtracted the completion of the square in situ, in the place, right? It's just like adding 0. But negative 16 plus 11 also simplifies, since they're like terms, and we get x plus 4 squared minus 5. And so where's that vertex? Well, the vertex, according to our model of our standard form, is equal to the point negative 4, negative 5. And all that is just completing the square right here, and recognizing that, well, if we have a situation where we can set up a perfect square trinomial, we should. All right, let's try it with a different one. This time, very similar. Well, in this case, we've got something that isn't equal to 0 or 1 in front. A little bit more difficult. So let's demonstrate how we're going to do that. We want to find the coordinate of the vertex in the axis of symmetry. Oops, sorry. I need to find my axis of symmetry. My axis of symmetry in this case is going to be the line x equals negative 4, right? It's a vertical line. Always takes the form of the equation x equals a something. And so this is my axis of symmetry for this graph. All right, let's talk about the next one. We've got y equals negative 1 times x squared plus 2x plus 4. as the general form of this equation, and we need to get it in standard form. So what am I going to do? I'm going to take this equation where I have y, and I'm going to factor out 1 for my two terms that have x, because I only want positive 1 as my leading coefficient anytime I'm going to complete the square. So I will have x squared minus 2x in parentheses plus 4, and you might recognize that that is the same as the function above it. The advantage right here is that I have the expression x squared minus 2x, and I want to complete the square with that expression. If I have x squared minus 2x, we ask, well, what number could we add to make it a perfect square trinomial? Answer, divide 2 by 2, take half of the x's coefficient, square it, and add that to the end. So in this case, we want plus 1. But remember, we can't just add plus 1 from nowhere, right? We have to do something to keep the equation balanced. So we want to make sure it's like we're adding nothing. So we're going to take away 1 at the same time. And I know you're shaking your head going, why? Why, Mr. Peoples? This is dumb. You can't add negative, positive 1 at the same time. You're just adding 0. You're not changing it, and it's just going to ruin everything I'm doing. Okay, deep breath. Right? You would agree that as an in-between step, if I wrote to you y equals negative x squared minus 2x plus 0, it would be exactly the same as the equation you just started out with. The only difference in what I'm doing and what this is that I'm adding positive 1 and negative 1 at the same time. And the reason why I want to do that is that this guy right here, this negative 1 that I added on along with the positive 1, is something that I want to take out somehow from inside these parentheses, so I have a nice perfect square trinomial in parentheses. So I want to add this, or I want to take this expression out of the parentheses. So how am I going to take negative 1 out from inside of a parenthesis that has negative 1 in front of it? Well, the answer to that one is that if I were to use my distributive property, I would have to multiply negative 1 by every quantity inside of the parenthesis. But I'm only going to distribute it to one piece of the parenthesis. I'm going to take that negative 1 from here, x squared minus 2x plus 1, and I'm going to take that negative 1 and distribute it to this last term, so it becomes plus 1. Right? Why? Well, again, remember that in fact what you're doing right here is you're treating this by using your distributive property so that you have negative 1 times the quantity x squared minus 2x plus 1 minus 1 times minus 1 plus 4. And you'll notice what I did was I just took negative 1 and I distributed it to all of the terms, only this time I'm just distributing it to the very last term. Looks kind of weird, but okay, trust me on this one. What we're going to get is negative 1 times our perfect square trinomial that factors as x minus 1 quantity squared plus 5. So where's that vertex? That's right, 1, 5. We know that the axis of symmetry is going to be x equals 1. And so we're done. That's what we wanted.